So, hey, I just want to remind you to watch the video right before this, video 35, where we depress the freezing point of seltzer water. Okay, so if you haven't watched that yet, it's just like 2 minutes long. I think you'll think it's kind of neat. So, hey, we're gonna look at a little more careful. We're gonna look at colligative properties today. So we want to concentrate on this situation right here, where we're dissolving 42 grams of sodium chloride into 500 grams of water. Okay. So we know sodium chloride is really soluble. When the sodium chloride goes into the water, what will happen is the water molecules will break apart the ions. And so what we'll have is, if we have a sodium ion, that would be surrounded by some water molecules like that. That's ion dipole. That would be the attractive force, the name of the attractive force, an ion dipole. Of course, the chloride would be surrounded by the hydrogen portions of the water molecule. Okay? So let's think about this boiling. So we know that water typically boils at 100 degrees Celsius. Okay? Or 100 degrees Celsius. So that's just boiling point of water. All right? Well, whenever we add something to water, whenever we add anything to water, what happens is the boiling point is elevated. And I think it's easy for you to understand why. If you think about water boiling, so the water molecules would have to turn from a liquid to a gas. And for that to happen, it needs to absorb a lot of energy. Once it gets to 100 degrees Celsius, normal boiling point, it'd have to absorb, what's the heat of vaporization? 450, I think, calories per gram. So in this case, though, so for this water molecule, or let's look at another water molecule. For this water molecule right here to turn into a gas, it's got to break away from other water molecules. That's hydrogen bonding. Now, if there are only other water molecules in there, then it would boil at 100, as long as the pressure is 1 atmosphere. But in this case, there's another attractive force keeping the water molecules from turning into a gas. And that's this ion here. So not only does this water molecule have to break away from lots of other water molecules, it has to gain a lot of energy to turn into a gas, needs to break away, needs to break the hydrogen bonds. It also has to break the ion dipole bond. So boiling point is elevated. Let me just write a dotted line here, okay? We'll figure out what that temperature is. We're not sure what that is yet. All right, freezing point. If we were to put this in the freezer, normal water would freeze at normal temperatures at 0 degrees Celsius. But from the video, from watching the seltzer, whenever you add something to water, it depresses the freezing point. So in the case of seltzer, that was carbon dioxide. So freezing points are depressed. And so now notice the liquid phase, the liquid state is increased. So boiling point goes up, freezing point goes down. Whenever anything is added to water or a solvent, that happens. Boiling point's elevated, freezing point's depressed. Okay? All right. So what we want to do now is quantify this. Let's first figure out what the freezing point of this solution would be. We're going to keep working on this solution. So here's a new equation, okay? The change in freezing point, delta freezing temperature, is equal to some constant. It's the molality freezing point depression constant. Yeah, it's a lot. It's just a constant. Like R is a constant in pivot. Times little m times I. Okay, notice I'm using little m, not capital M. Capital M is molarity. Little m is molality. It's another unit of concentration. And in colligative properties, I think it's the only time we use molality. So you'll get used to using it. But that's the equation. I stands for number of ions. It's actually called the Van Hoff factor. I'm not going to write that down. Let me write down number of ions. In this case, with sodium chloride, the sodium chloride will break apart into 2 ions. So I is 2. In the case of like sugar, sucrose, or any type of sugar, it's covalent. It's not going to break apart into ions. So I is 1. If you think about, let me write something here. Think about aluminum chloride. When that dissolves, it'll break apart into aluminum ion and 3 chloride ions. So look at that. I would be 4 in that case, okay? So the more ions, the lower we can depress the freezing point, or the higher we can elevate the boiling point. Okay. So let's go ahead and calculate this. So delta TF equals, now, the constant for H2O, for the solvent, is 1.86 degrees Celsius times kilogram per mole. Now don't worry about that. I'd give that to you, okay? I'll give that to you. That's unique to water. That's the molal freezing point depression constant. Okay, let's calculate the molality. Okay, molality, let me do that right here. Molality is equal to moles of solute over kilogram of the solvent. So the moles are the same as molarity, but this is what's different. Instead of having liters of solution, it's kilograms of solvent. So just think of molality, little m. There's a lot of m's in chemistry. Molecules, moles, molar, molybdenum, molarity, molarity, a lot of m's. Just think of molality as moles per kilogram, okay? So if you think about 500 grams, of course that's 0.5 kilograms. Now what we need to do is convert that to moles, all right? So 42 grams of sodium chloride. Let me get a calculator, okay? It's 22.99 plus 35.45. 22.99 plus 35.45, that's 58.44. This is 58.44 grams, 1 mole. Okay, so we'll just get that answer, times 42. This is 0.7, let's say 19 moles per, it's just moles, okay? Let's put that up here, 0.719 moles. The I is 2, so we're going to multiply it by 2. Remember, sodium chloride is made up of 2 ions. Sodium ion, chloride ion. That's the 2. And then if we do that, we'll just multiply. I'm going to divide this. Divide by 0.5. See what that equals. Multiply by 2. Multiply by 1.86. Hopefully this is what I got earlier. So the answer is, let's look at the sig figs. Hey, there's really only 1 sig fig here. So I should round this to just 1. So it's 5 degrees. That's the change in freezing point. So back to this question, what temperature will this solution freeze? Instead of it freezing at 0, it's going to freeze at -5 degrees Celsius. So the answer is -5 degrees Celsius. That's the answer. That's the temperature at which this solution would freeze. All right, so this is new. This is new right here. If it's boiling point elevation, we'll have a different constant. We make that a B. We still have molarity in I. This is new as well. Molality, little m, is equal to moles of solute per kilogram of solvent. What makes this a colligative property is that the only thing that dictates the rise in boiling point or the lowering, the depression of the freezing point is the number of particles. Okay, the number of particles, the concentration of those particles. And hey, look, as you go through this, you may need to pause every once in a while just to familiarize yourself with a couple of new things that we learned. Boiling point's elevated, freezing point's depressed. This liquid portion, this liquid state is increased. Okay, and that's that. Hopefully that'll help you. Bye-bye.